Hello, welcome to another physics video. Today we're going to be looking at specific latent heat, and the three things we're going to be doing are we're going to name the changes in state and explain what happens at the particle level. We're going to define the term latent heat, and then finally we're going to use the equation Q equals mL to calculate energy absorbed or released during changes in state. So a nice place to start when we're talking about changes in state is just a quick recap on our structures of solids, liquids and gases. Okay, so we can, if we remember now, a solid, I want you to think of now the perfect fire drill on the yard. Okay, every pupil standing in a nice row, everybody in equal columns as well. Everything is very ordered. You'll notice in this diagram that first of all they're very close together. They're all particles are almost touching. And it's in a very regular pattern. Okay. Now the big thing that we need to recognise is even though they are very close together and they are touching, they are still moving. They are vibrating, albeit quite slowly, but they are vibrating. We then have liquids. Now, a bit like a solid, they're close together, but now they've kind of started mixing up a bit, okay? Now, the key thing about a liquid is that even though they are touching, these particles can slide over one another, okay? They are able to move, which explains why things like a liquid flows, okay? And finally, we've got a gas. Now, a gas, we can see that the particles aren't touching. The main thing is that they're in a random arrangement and they move in different directions, okay? So they're not bound together at all. There are no bonds holding a gas together, whereas in liquid and solid, we have got bonds holding those particles together. Now, this diagram here shows us the 6 changes in state between our 3 states of matter, those being solid, liquid, and gas. Let's start with the most simple ones. Melting and freezing. Melting is where you go from a solid to a liquid. Think of ice melting to water. And freezing is the opposite. Water to ice. Or a liquid to a solid phase. Okay. We'll then go to ones perhaps where we've encountered before. Let's talk about condensation and evaporation. Now these are, first of all, evaporation is when we turn a liquid into a gas. Think of steam here. If you boil a kettle, you get gas coming out of the top, that is steam. And finally condensation, okay, where we're going from gas to liquid. Example of condensation would be rain, okay, whereby water vapor in the upper atmosphere turns into a liquid and condenses into rain, okay. Now 2 which perhaps we haven't seen before are sublimation and deposition. Now sublimation is where we go from a solid to a gas. Now this is quite rare. Maybe a nice little story I can tell you about sublimation is that during Victorian time, a lot of people would have arsenic wallpaper. Okay, and arsenic, which has got the chemical symbol AS, famously sublimes. Okay, so what was happening is that people would have solid arsenic, making their wallpaper lovely and green. It would then sublime into a gas and they would breathe in arsenic, and then that would cause them to get poorly with arsenic poisoning. So sublimation, solid to a gas. Our last one, gas to solid, is called deposition. So deposition is gas to solid. The classic example of deposition is frost. So water vapor in the air very, very quickly skips the liquid phase and turns straight into a solid as frost. Okay. Another example is if you watch cooking shows and they get liquid nitrogen. Okay, you will notice that liquid nitrogen appears to have like a fog around it. Now what liquid nitrogen is doing there is turning water vapor in the air, because it is so cold, into solid ice, tiny particles of ice. So let's talk about what's actually happening at the particle level during these processes. So let's first look at during heating. And during heating, I'm talking about melting. I'm talking about evaporation. And I'm talking about sublimation. Those are my three processes. So first of all, for any of those to happen, a substance absorbs heat energy. Okay? And when this happens, those particles which I showed you in that initial diagram, they begin to vibrate more vigorously. Okay? Eventually, they vibrate so much, they move so much, that those bonds keeping them in place start to break. So think with a solid now, we were really, really ordered. I've started moving around so much, I'm breaking that force which is keeping me in position. And finally, when we break those bonds, the substance changes state. Okay, so that could mean I could go solid to liquid, liquid to gas, or solid to gas. Now, if we're talking about during cooling, I'm now talking about freezing, condensation, or deposition. And it is the complete opposite of heating. So during cooling, a substance releases heat energy. Okay, so some of that energy is getting rid of. As it releases that, the particles in that substance have less energy, so they don't vibrate as much. In fact, they vibrate more slowly. Eventually, they stop moving so much that those forces, those bonds which were broken, are now able to reform. Okay, those particles have calmed down. They can now be brought under control. Okay, and when they get brought under control and those bonds reform, we get a change in state. So we're talking about things like liquid to solid, gas to liquid, and gas to solid. So that is what's happening at the particle level. Some really key concepts there, some key points for you to know. So specific latent heat, what is it? Okay. Well, normally what I want you to think is if we heat something up, the temperature rises. I think that's quite a simple concept. If you put a Bunsen burner underneath a beaker of water and you heated that water, you would expect the temperature to rise. It'd get warm quite quickly. But specific latent heat is the heat energy required to form or break bonds during a change of state without changing temperature. Okay? So when we're talking about latent heat, we're talking about when we're heating something but the temperature isn't increasing. Now, a classic part of this is that water can never go above 100 degrees, okay? Because as soon as we get to 100 degrees, the bonds begin to break, okay? So I want you to think specific latent heat is all about the heat required to break bonds. So, for example, if I'm going from water to steam, I'm breaking these bonds which I'm drawing a blue line between now. Okay, so this is what latent heat is doing. The heat isn't increasing the temperature, it is breaking all of those bonds. Okay? So how do we calculate specific latent heat? Well, with a nice equation of this, it is Q equals M times L. And in this, we've seen Q before when we've done Q equals mass times specific heat capacity times temperature change. Again, Q is energy. And when we're talking about energy, we're talking about kilojoules. M is mass. So that could be your mass of water, could be your mass of copper, your mass of iron, anything. It is your mass, and we're talking about kilograms. And then L is our specific latent heat. And this is in kilojoules per kilograms. For those of you which like to use an equation triangle, the equation triangle is there. That might give you a hand now, because I am going to ask you to rearrange in the quiz. So that is going to be helpful for you. Let's look at calculating latent heat then, using that equation. So the first thing, calculate the heat energy absorbed when 200 grams of water boils with a specific latent heat of boiling is 2260 kilojoules per kilogram. First thing then, my mass is 200. My latent heat is 2260. I've got them in kilograms and kilojoules per kilogram, so I don't need to do any converting. They've asked me to calculate heat energy, which is Q. So I'm going to do Q equals M times L. Swap my numbers in. I'm going to use a calculator to do this, okay, to make no silly mistakes. And this is going to give me 452,000 kilojoules. Okay, I'm going to make sure I've got my units. Just for a second example now, calculate the heat energy released when 25 kilograms of water undergoes freezing with a specific latent heat is 334. Again, they're asking me to calculate heat energy. So my mass equals 25. My latent heat equals 334. I'm going to be doing the same process again. So Q equals M times L. Q equals 25 times 334. Again, use that calculator. Don't make silly mistakes. This is going to give me 8350 kilojoules. Thank you for watching. Hope this has proved helpful. If you've got any questions, make sure you ask your physics teacher.